about the integration by mass reduction for unitarity.
Okay, so thanks a lot for inviting me to this very nice workshop. So today I'm going to talk about the new development in the IBP reductions from the viewpoint of unitarity and some algebraic geometry techniques. So this talk is based on the work with my collaborator, Kasper Larsen, and also student Alexander Zhang. So I think, in some certain stage of working on scattering amplitude, we heard of the IBP reduction. Okay, so in principle, it looks quite simple. It's just linear relations between the loop integrals. For example, there's a quite simple one. Okay, if you start with this kind of double box integral with some numerator, you can say that you can rewrite the whole thing as a list of so-called master integrals. Okay, I just name this kind of master integrals with this kind of red words, and also get some quite complicated coefficients. So in the real life, okay, for example, if you consider multi-loop or multi-legs or massive theory without supersymmetry, you will find that actually these kind of coefficients are quite complicated. And in order to get this kind of complete reduction, it takes a lot of time or maybe computer resources. So in many kinds of amplitude calculations, really a bottleneck. So in this talk, I'm going to say something about from the mathematical view, especially the so-called tangent algebra of affine varieties, to study the property and to derive this kind of IBP relations efficiently. So the mathematical object actually is quite simple. You start from some kind of geometric object, I call it affine variety. It could be a curve, it could be surface, it could be hypersurface. Okay, then you study the tangent vector fields defined, globally defined, but tangent to this geometric object. If this geometric object is smooth, then basically it's quite a trivial question, because it's a differential geometry question. But in real life, for the amplitude study, this kind of variety could be singular. So in this case, we worry about how to define this kind of tangent vector field around single points. And in this case, it's an algebraic geometry question. If you can get this kind of tangent vector field, you can easily get the IBP relations you want. So that's the whole idea of this talk. So first, what is the IBP reduction? So IBP reduction itself is very simple. If you work with a d-dimensional regularization scheme, you will find that, if you consider the total derivative, then you can set it integrated to 0 in this case. So if you calculate some kind of high loop or high multiplicity amplitude, you will find that, in general, you will have some kind of complicated integrand like this. This one is a quite a huge numerator, possibly from the gauge theory with thousands of terms. But you only have a quite small subset of the master integrals. That means you have a lot of linear relations to reduce the whole thing to master integrals. Then you can apply some symmetry relations, some kind of dimension shift, and also most importantly, the IBP relation. Here, that's a quite a typical example when you try to calculate amplitude. So maybe you start from some kind of integrand. So to get this integrand, you can use some Feynman diagram approach. Or you can make a shortcut with the integrand basis. So by the integrand basis, that means you make an ansatz of this kind of integrands with the coefficients undetermined. Then you try to fit all the coefficients by various unitarity cuts from tree amplitudes. And again, get a complicated integrand. So after getting the integrand, maybe you need to run the IBP. Suppose the integrand is too huge, and then you run the IBP to get a quite a small number of the terms, the master integrals. And then the next step is, you have to evaluate this kind of master integrals to get some kind of analytical results or numerical results. So one typical scheme is you need to consider the differential equation for the master integrals. So for this part, I refer to the very nice talk by Smilov on Monday. So you see, if you consider the differential equation for master integrals, you find that after taking this kind of differential operators, you will get a new list of integrals. Then you have to reduce the back to the master integral to get a closed differential equation system. So for that step, the IBP is also necessary. So we know that if you consider high loop, IBP actually is quite difficult. The reason is very simple, because here you see if you consider high loop, then this differential operator have many different choices. And also, to close this kind of Lorentz index, you have to put in some kind of vector. This vector is called the IBP generating vector. So you have so many different choices of the vector. You have so huge number of IBPs. Then you get quite a big linear system of IBPs. To get the particular IBP you want, you have to do something like a Gaussian elimination over this huge linear system to get the result. So from the introduction of the IBP relation almost 35 years ago, there are already several public codes like file, reduce, and light read on this subject. But I have to say that for some quite complicated two-loop or three-loop diagrams, okay, we still need to somehow in the future improve the efficiency of generating IBPs to consider more complicated kinematics or higher loop corrections. So I mentioned that about 6 years ago, okay, by David Casper and his collaborators, there's a new approach from IBPs. This is called the syzygy method. So the syzygy is some kind of criteria to restrict the number of IBPs. So that's a criteria to tell you which kind of IBP is quite good, which one you don't want to consider. So we'll get a quite smaller linear system, and you don't need to run this kind of huge Gaussian elimination to get the IBP you want. So basically, my talk today is also using this kind of syzygy approach. Also, I have to say that for simplifying this kind of IBP system, you can also apply the highly efficient finite field method. So I refer this point to Shambhika's talk tomorrow. Okay, so here's the outline of my talk. So I will present a new method of generating the IBPs you want. Okay, so I just give you some kind of good IBPs. Maybe you can apply in the computation. So this new method coming from 3 ingredients. The first one is unitarity. So instead of getting all the IBPs at once, I do it from the various unitarity cuts, and then I try to reconstruct the full IBP from this kind of cut information. I think in each case you have a quite small system to solve, so it's more efficient. And the second ingredient is this kind of algebraic geometry understanding of the syzygy equations. Then we try to somehow apply this kind of syzygy equation in an efficient way to further reduce the number of IBPs. The third ingredient may be less familiar for the audience, so this is so-called Baikov representation. It's also a way to parameterize your loop integration. Okay, so we think that this kind of parameterization will give you the quite easy control of the unitarity cuts, and also the syzygy equation in terms of the Baikov variables looks quite simple. So we decide to use the Baikov variables. So this talk is actually based on the 2 papers with my collaborators, Kasper Larsen and Alexandru Georgodis last year, and a new paper to appear maybe this month sometime. Okay, so here's the setup. So this setup is coming from the paper from last November, and I also refer to Harada Itai's paper for the similar parameterization and the idea of using syzygies to reduce the number of IBPs. So here in this picture, there's nothing fancy, everything is standard. So you start with the dimensional regularization. Okay, you put all the external momentum in the 4D or any kind of integer dimension. So for the internal momentum, you split that into 2 pieces. One is the 4D part, the other part is the extra dimension part. And then you introduce some scalar products over the extra dimensional part, which is mu1, 1, mu2, 2, mu1, 2, if you consider 2 loop. And you have to consider mu_ij, symmetrical mu_ij product for higher loops. So by doing this, you find that the first change is here you have a unfixed number of variables, because d is just some parameter. We have 2 d variables for 2 loop. But after using this kind of dimension split, you can say that you only have 8, actually. 8 plus 3, so 11 variables in total. So we control the number of variables. Here, okay, by changing the variables, you are introducing this kind of manual form in the integration. So this one is just quite familiar, the dimension shift operator. Okay. This is determinant of the mu variables. If you consider higher loop, that the formula is almost the same. Okay, you just have more mu's. So instead of this kind of 2 by 2 determinator, you have L by L determinator. And also this power is changed, okay, according to the number of loops. So here's a further shortcut. Okay, so this one is also quite simple. If you consider some diagram with n external length, okay, suppose n is quite small, less or equal than 4. So in this case, you will say that you can have 5 minus n orthogonal directions, or we call it spurious directions. The direction is perpendicular to all kind of physical external momentum. So in this case, you can integrate out all these kind of directions. Then you further reduce the number of variables. Okay, you can see here, you can reduce the number of variables. And also the power is changed. So that's a shortcut for our calculation. We are going to use that for our this kind of 2-loop 4-point example. So in the rest of the talk, okay, to be more specific, I will focus on some example, maybe 2-loop with 4-point. But actually, this should work on any loop or any point. So I start with a kind of simple one. It's a double box 2-loop example. For this example, okay, I can continue to consider this kind of IBP reduction, but before this kind of reduction, let me introduce this Baikov parameterizations, because I think that will simplify the IBP computation. The thing is, for this diagram, you see there are 7 properties. Okay, but if you count the number of the integration variables, so from here you get 11 for the 2-loop. From this kind of orthogonal direction, you can remove 2 orthogonal directions. So in total, you have 9 variables. 9 variables here. So you have to introduce 2 additional variables to match, okay, this kind of properties and the integration variables. So this idea of Baikov. You can introduce 2 ISPs, irreducible scalar products, Z8 and Z9, complete the system. And then you make the change of variables from this quite common variable of this L and mu variables to Z variables. Okay, the Z1 to Z7 just the inverse properties, and the Z8 and Z9 the additional ISPs. So definitely this one is a nonlinear transformation, it's a quadratic transformation. Okay, because Z is a quadratic function of this L. But you can prove that by construction, this Jacobian is always a constant. Okay, then in the fancy language, if you have some kind of polynomial map such that the Jacobian is a constant, and especially if the degree is at most 2, actually the simplest case of the so-called Jacobian conjecture. The Jacobian conjecture itself is an open question, but the degree 2 case is already proven. So you can see by Jacobian conjecture, the inverse map exists, and the inverse map is also polynomial map. So it's a solid parameterization. You can change everything to the Z variables. Okay, so you will change the integrand like this. So you can say immediately here it has some quadratic functions with d's, but after this Baikov parameterization, everything is linear. If the denominator is linear, then you find that all this kind of cancellation between numerator and denominator becomes quite trivial. So immediately, okay, the advantage is you can do quite simple, so-called adaptive integrand reduction by Australia and his collaborators, okay, in the spring, this integrand reduction. And also you can say the advantage is it's very easy to apply any kind of unitarity cut, maximum cut, non-maximum cut, any kind of cut. Because if you consider cut on this direction, then you still have to solve some quadratic equations to get this kind of cut branch. But if you change it to the Z variables, actually it's very simple. The Z variables are just linear things. You just solve a linear equation. You can get any kind of cut you want, so it's quite easy to control the cut. So that's the reason we choose this kind of parameterization. And it also works for nonlinear, this kind of non-planar diagrams. So as a toy model, suppose instead of doing this kind of complete IBP reduction, we can try the maximum cut version of the IBP reduction. So the thing is, I said, okay, you change all this kind of denominators to delta functions, but here the trivial delta functions because a linear argument in the delta function. So after integrating all the delta functions, get a two-fold integration like this, very, very simple. Then just try to say, if I have a complicated numerator here, so how do I simplify it? Of course, it's when there's a two-fold integration, you can just integrate it out the remaining z8 and z9, these two variables. You should get some kind of hypergeometric function in D, and then you can use the relations between hypergeometric functions of D to derive the IBP relations. But we think that is unnecessary because that's a very simple example. In a more realistic case, we have some kind of massive scales or high loops. You don't want to introduce more and more complicated special functions to do the IBP. So instead of doing this kind of thing with direct integration, let's consider this kind of IBP just by answers like this. You introduce this kind of total derivative. It's alpha 8 and alpha 9 as just two arbitrary polynomials, and you consider what kind of IBP you'll get. So to make the things more interesting, we can introduce some kind of math scale into the system to see with fully massless or one mass or two mass case. So how does the solution will be different? If you just naively expand the IBP relation, you find that's not quite good. That's quite a bad term here, because you take the total derivative of the f, then you introduce this kind of dimension shifting again, then you get a correct IBP, but the integrals are in different dimension. Okay, that's quite a bad situation. You don't want this kind of IBP. Then the trick is again to use the syzygy method to control the IBP. You just require this term is proportional to f. If it's proportional to f, that's very good. You can see that the dimension shifter is gone. Then you just need to solve this kind of syzygy equation. So this syzygy equation, actually the special kind of syzygy equation, is coming from only one polynomial f and the first two derivatives of that. Then we can consider the geometrical meaning of it. You can rewrite out this kind of syzygy equation as an operator equation, this kind of differential operator or vector field acting on the function f. The result is proportional to f, or somehow the idea generated by the f. That one is called so-called actually the tangent algebra of the affine variety defined by f. It's an infinite dimensional Lie algebra, and also it's a module over the polynomial ring, so it has quite a rich structure. And you see, you try to solve this kind of syzygy equation, then you better consider just this f equals 0, what kind of geometric object you will get. For the math case, okay, actually it's quite complicated. You will get a reducible curve with 3 singular points. For the one massive case, you get one singular point. For the massive case, actually is quite simple. You get an elliptic curve that's smooth, no singular point. Actually, these 3 polynomials together is a so-called singular idea. If you solve the singular idea, when there's no solution, you get a smooth curve. Now the question is, how do you find the tangent vector fields about this curve? Okay, so again, intuitively, if the curve is smooth, it's quite a simple question, a differential algebra. Only when you have some single points, it's more complicated. So let's translate everything to the algebraic geometry language. So if you find that this f, okay, it's a matter form, okay, a smooth geometric object, then that means the singular idea has no solution. Okay, then you can apply this Wheeler-Sussman theorem. That means the tangent algebra is a free module and generated by principal syzygies. So actually, it's just the intuitive picture. If there's no single point, it's very easy to find the tangent vector field. So for the massive case, actually you can find this kind of syzygy solution just by hand. You don't need to do any kind of calculation. And for this kind of massless case or one mass case, you need some calculation. But anyway, here is just some kind of geometric explanation of solving the equations. Actually, you don't need to understand in detail how to solve this kind of equation, because you can just apply some computational algebraic geometry software like Macaulay 2 or Singular to do this kind of synthetry calculation. But just keep in mind, okay, inside the algorithm of Singular or Macaulay 2, they really consider different kinds of geometric pictures. They really distinguish with the different types of solutions, whether free module or not. Suppose that you get this synthetry solutions, then you can get all this kind of on-shell part of the IBP just quite easy because you already get rid of the bad IBPs. You can also do maximum cut for more complicated diagram if you do this kind of 5-point diagram. But in this case, you say you don't have the spurious direction, then you have 11 variable questions. So after 8 cut, you get 3-fold integration. You can again apply some kind of ansatz over it to consider the bigger synthetry equation. This synthetry equation is more complicated because it's tell you have to solve for the tangent algebra for the surface, but again can solve it by Singular or Macaulay 2. So we are going to publish a small package called Zoolite just to do this kind of maximum cut version of the IBP. So for that one, it had two purposes. One is to find the list of mass integral automatically, just like me. But we think that our approach is quite fast because we just consider a small subset of IBPs. And also it will give you maximum cut, the explicit form of the IBPs. And the more important thing is to consider the non-maximum cut to get the full IBPs. Then you have to release some of the cuts. For example, you only do this kind of 5-fold cuts. Then you have 2 propagates which are free, not on the cut. So in this case, if you consider synthetry equation, you find that you can apply 2 additional conditions about this Z3 and Z6 to get rid of the double propagates integrals. Then you can reduce the number of the IBPs. I don't mean you really excluded all this kind of double propagate integrals from your system. So I just mean here you try to reduce the IBP system such that you can reduce all this kind of low double propagate integrals to master integrals. So afterwards, in the real life, if you have double propagate ones, you can just get it back, consider this kind of double pole, and put it into this system and get the reduction of the double propagate ones. Okay, so here you have a list of synthetry equations. The geometric meaning is consider the tangent algebra of this surface defined by this 3, this 6, and the measure equals to 0. Of course, this means a reducible curve, or reducible surface. You can solve the tangent algebra by software, and you can get the reduction to the double box and also slash the box. You release the 2 cuts to have more master integrals. But actually, from mathematical viewpoint, it's not very good to solve the whole thing together, because this one is a quite a singular surface, a quite singular curve. It's reducible. So in this case, you'd better solve them separately. You do the primary decomposition of the whole surface of the whole curve. You solve them one by one, and then you solve for the first one, you get one tangent algebra, and you solve for the last 2. Then you consider the intersection of the modules. For the intersection of modules, you can do it by the standard algorithm by group basis. So after doing this, taking the intersection, you will get the whole tangent algebra. It's much more efficient than to solve them directly at once. So let's talk about the complete reduction. So to get the complete IBP, we really need the lowest master integral. Just recall that we can use our package to get the full list of the master integrals. So we just look at the full list of master integrals to find the master integrals with the fewest number of properties as the lowest master integrals. There's 2 subsets and this double bubble and this bubble triangle. So for each one, for example, this one, we do a 3-fold cut. Then we can recover some of the coefficients, and we can do a 4-fold cut, and this kind of triple cut, and the quantity cut like this. We have to make sure that for each step, For example, we get two mass integrals, okay, actually the two mass integrals are identical. We have to make sure that the two coefficients are the same, otherwise something wrong in the calculation. We suppose that all these kind of coefficients are consistent, then you can just merge all the results to get a complete IBP. And it's quite easy to parallelize this kind of method because the different cuts are just independent. Okay. So here, some timing for this algorithm by doing this kind of complete reduction. So we can do the double box diagram, the math in this case. Okay, suppose we have some kind of numerator with a rank up to 4, can reduce all these kind of numerators, okay, all of them at once to the 8 mass integrals in only 39 seconds. And if you introduce one mass to a diagram, okay, still quite fast. You can reduce all this kind of numerator up to rank 4 to 19 mass integrals in about 160 seconds. So that's just some quite a primitive implement in mathematics and singular and Macaulay 2. So here's a summary of my talk. So in this talk, I just presented a new method to generate the IBP relation efficiently based on unitarity and algebraic geometry method. And it works, okay, for arbitrary kind of unitarity cut. So if you suppose you don't want to complete the IBP, then just run our algorithm partially, get the partial result you want. If you want to get the complete IBP, just consider all the possible lowest diagrams and run this kind of algorithm merge together to get the complete IBP. Of course, there are some further directions we can consider. One thing quite interesting is we can consider the wire algebra and the D-module structure of the IBPs. So here I already say this kind of synthetry will give you some kind of different operators. So you have this kind of Lie algebra structure. But what about just consider the whole thing as a wire algebra and consider this kind of integrand as an element in the wire algebra? Then instead of considering linear algebra to this kind of reduction, you can just consider the left or right idea generated by the operators. Then you do this kind of reduction in this wire algebra. You just reduce your target integrand towards this idea in wire algebra. You should get the result immediately without using any kind of linear algebra techniques. And also, if you consider large D limit, then you find that this non-commutative algebra is less and less apparent. It becomes more and more commutative. So if you consider large D limit, you can see that large part of the IBP, and not just the D module, actually it's just the common module, the commutative module. So if you consider large D limit, things is getting much simpler. And also for the programming part, here we did something like really it's cut to the bottom. We consider kind of threefold cut. And then maybe for the programming purpose, it's better to do it one by one. So instead of considering maximum cut or this kind of minimal cut, we can consider some intermediate steps to one step further recursively to get the whole result. Could be more efficient. And also somehow we can take some interference between the two different directions. For example, we don't need to calculate the same coefficients in different directions. And the final goal is to get a fully automated and efficient algorithm for the IBP generating. Thanks for your patience.
Any questions for Jan?
So first of all, very nice talk. I was wondering, do you have any timings for the non-finite double box? You know, just with no masses anymore?
I have some examples for that because I just did some kind of various cut, but I didn't merge the whole thing together. But my feeling is just from the maximum cut and the sum of the non-maximum cut. I think for the non-planar case, it's not that difficult. I don't think it's.
No, it should be.
It should be almost the same.
I just wondering if it's the same or different.
Almost the same, I
The
see.
usual approach, you see the linear algebra is much more complicated for non-finite sectors. I just was curious if it
I
shows up.
think for our case, it's not getting so complicated because. Yeah.
All right.
Okay.
And then the other question maybe is, what steps remain for towards the goal of full automation?
Uh,
Towards the goal of full automation of the algorithm?
Oh, there are several things because we try to do things step by step. So first we try to get this part ready, which is the C, to get the complete list of master integral this part ready. So we try to publish this package first, and then somehow we try to combine this zero-right package with the current algorithm, so and read the output of this master integral list for the result like this. And of course, okay, if you say the computational side, okay, if you consider everything numerically and do the computational algebra geometry, actually it's quite straightforward. But if you will consider the analytical calculation, especially you have a larger number of parameters, then there are several tricky things you need to worry about. For example, you will find that the ordering of the module or ordering of this polynomial ring is quite important for the speed of the symbolic calculation like this. Okay, and also for the intersection method, you will say that, okay, so how to apply this kind of intersection? Okay, because this one is associative, then this ordering of the intersection is also something you can tune. But right now it's not fully automatic.
Next question. Can you go back to the last slide with the time?
Yes. Yes.
So do you have any, so what is compared here is absolute numbers, but do you have any comparison to Phi or reduce?
Because I would say it's a little bit hard to compare because right now our algorithm is not parallelized yet, so we only use one CPU and this laptop memory to do this kind of computation. So I guess that if you run file, maybe the C++ version from this kind of rank 4 case, maybe in parallelized mode, definitely can finish it at in similar time, I think 1 minute. But I think so far from all the experiments we used with Phi, I think our time for this one is faster, and also it's faster for that Phi can finish this kind of reduction. Okay, in our experiments about 200 seconds or something like that. It's always faster.
I'm running a bit late, so maybe further we postpone to have a discussion. So let's thank Jan again.
Let me say something before the coffee. So